The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone. Thank you for joining us today for a new indexing technique for quickly fuzzy matching entire dataset records. Dan Kemper, a dramaturg at HPCC Systems Solution Lab, will begin in just a few seconds. As a quick reminder, a brief survey will follow the end of the session. Use hashtag ODSC East to share the sessions you're excited for on social media, the speakers who inspire you, and the most memorable moments for a chance to win an Apple TV, All Access Pass to ODSC Euro 2022, and other cool prizes from ODSC partners. All the feedback helps us shape future conferences. Please join me in welcoming Dan Kemper. We will now begin the session.
Hello, everybody. Good morning, afternoon, good day. The title of this is a mouthful, and I want to clarify what it is if you didn't read the text that was associated with the talk. We're going to talk about how to more easily try to match entire records from datasets, from database records, comparing them to other database records when they don't exactly match, trying to link them up. Again, my name is Dan Kemper. I'm a thaumaturge, not really. I'm actually an enterprise architect for LexisNexis Risk Solutions. It's easier to just adopt a shorter title. It's also a good conversation starter. I've been with LexisNexis Risk Solutions for about 8 years now, working in their big data groups. We're in the solutions lab. Get to invent a lot of interesting things. And that's one of the things I want to talk about. We did some innovative research into this matching idea and came up with some pretty good solutions. So I want to get right into it. Oh, and before I forget, I do want to say that inside the Q&A chat, I did post a link to a PDF version of this presentation, so you can download it from there. The very last slide or the very last page of the presentation is an appendix with some hypertext links off to various things that I talk about here. And also one other thing is I believe this talk is tagged as machine learning. This is not a machine learning talk. There is no machine learning. So it's all going to be heuristics. That said, we'll move forward a little bit, providing I can, there we go. So anyway, I want to start with a little bit of background. So fuzzy string matching is basically the idea of taking two strings and seeing how similar they are. And the definition of similar is basically, do they share the same characters? Now, one of the canonical ways of doing that was the Levenshtein distance. It was invented back in 1966, and it measures the number of changes that you need to make to one string to convert it into another string. And by a change, I mean either insert a character, delete a character, or replace a character. It's good. It's the basis of an awful lot of string comparison algorithms. There's been a lot of research into this. There's been a lot of extensions. It's just a good base. The work that I'm going to talk about here begins with the Levenshtein distance. Now, part of the research into this had to do with speeding up the whole process. Computing a Levenshtein distance involves comparing character by character two different strings. When you've got a large dictionary to work through, that can be a very time-consuming process. So there's been a lot of research in how to make that go faster. Most of it has had to do with how to index things. One of the ways of doing this is this topic called a deletion neighborhood, which was termed, or I'm sorry, the phrase was coined back in 2007. And then there was some work done to extend that. But it was basically how to pre-compute a search index using this technique of deletion neighborhoods, which we'll go into in just a minute, and thereby performing basically a space-time trade-off. You build these very large indexes, but it pre-computes all of the fuzzy matches. So your actual search at runtime is an exact match, even though the results are a fuzzy match. You have to know, anybody who's played Wordle knows that a fuzzy match, when you're missing one character or you've got one character in a word that you don't know, opens up a lot of possibilities. You can wind up with false positives on this kind of searching. So what this really does technically is it reduces your search neighborhood. You might have 1 million words in your search dictionary you have to weed through. This technique allows you to take the 1 million and bring it down to 500, which you then have to exhaustively look at. So let's give you an example. We're going to start with a dictionary word example. So we are building the index for it. Now, a deletion neighborhood basically says with an edit distance of 1, which means we only want to make 1 change, the deletion neighborhood says we can delete 1 character at a time, and a deletion will perform the same kind of action as the replace, deletion, or insert of the original Levenshtein distance. So give an example, we first copy the word exactly, but then we go through and create variations of the word, deleting 1 character at a time. We can convert that to a hash value that both, encompasses different sizes of words and all that, and brings it down to a fixed length, which makes it easy to work with in computer terms. And we link those numbers back to the original word. That's the basis of a deletion neighborhood. Now, given a query word that's misspelled, somebody misspelled it, we run through the same process. Basically create a deletion neighborhood for it, create the hash values, and then we can easily join the two. And here we find a match, and that match maps back to the original word. This works. This example was a replacement example. So the E was, put in the query word instead of the A. If instead the dictionary word was examples, plural, and the query word was example, that would still work. You're deleting the S off the dictionary word, and obviously it would match the exact word put in. The other way around also works. Dictionary is example, query word is examples, plural. When you ran the deletion neighborhood, the S would fall off, and again, you would have an exact match. Again, this is edit distance of 1. If you had an edit distance greater than 1, instead of deleting 1 character at a time, you would delete combinations of 2 characters at a time. Your list of hash values would be much larger. So that's the basis of a deletion neighborhood. The academic papers that I cited actually deal with how to represent these very large lists of hash values, or the lookup variations efficiently, and how to search it efficiently. The technique itself is the same. So given this, what can we do with it? And this is moving on to what I'm actually talking about. So we have this idea. What we should do is re-examine the basics. So given a deletion neighborhood, we're working with a string, like the word example. What is it? That word, example, is the unit of information that we're interested in. It's composed of characters, but a character is really just a code value. It's an ASCII value, UTF-8 value, Unicode point value, or what have you. And they are combined. In this case, it's a concatenation, right? So let's redefine all of this stuff. So instead of a word, let's say we're dealing with a record. And instead of ordered characters, what we can do is order the field values within the record. Instead of the actual field value, or what is that field value, we'll make it a hash value. That'll turn it into a number. And then the operation, instead of concatenating, we're going to consecutively hash those field values. Now what that looks like, and this is just the first pass at this, what it looks like is a preparation like this. You take every field you're interested in and you hash its values. Then you can turn around and hash it left to right to come up with that value on the far left. Begins with 153. That's basically its fingerprint. And you map that back to a unique identifier. So that unique identifier throughout this talk, I may refer to as an entity ID rather than some other kind of ID. part of that is because of the research that we did to come up with this. We were working with people, so they were entities. But it can be anything. I mean, as long as you have a thing you are identifying, it can be an ID. It doesn't have to be a record ID. It doesn't have to be unique per row. It just needs to be unique per entity, thing you are trying to match up. So this was the first take. Now we do a lot of work in LexisNexis with people and their information. And one of the things that when you look at this, you realize these fields here, some of them really need to go together. Street suffix by itself doesn't add a whole lot of meaning to the records. So we need to combine things. So one of the things we added support for is this concept of a field group, which is just taking, one or more fields and you call them groups. You put them together and you treat them as one. So even though they physically exist in your data set as multiple fields, you bring them together as one. That's what's shown here. Street name, street suffix are put together. When you do that, you wind up with a different hash value. And it changes that fingerprint over there on the left. Now, once we have that, what happens if we run a deletion neighborhood? So that deletion neighborhood is going through and deleting with an edit distance of 1, the hash values, consecutively, hash values of different field groups. We're basically creating variations of that original record. And they all have different fingerprints over there on the far left. Now, once you look at this, the last line is basically saying that will exist another record that has a first name, last name, street number, street name and street suffix put together, and no city, state, and zip information is included, right? If you're actually searching for a person who lives at an address, not having city, state, and zip will change your results. You're going to get a lot of false positives, especially with a Jane Doe or a very common name, John Smith. By recognizing this, you recognize that there is some information inside your data set that you really need to never delete. So we added a concept called a required field group, which basically means we have a field group and we should compute the hash values and do all the normal stuff on it, but never delete it. And this slide is basically saying, hey, this last row, we're just going to ignore that. Looping back, now the original deletion neighborhood idea can be combined. And before you start this whole record set thing, you can run this, the per field version, before you ever do any other work. So if you think your first name field can be misspelled, you can process your data first by creating variations of these records where, in this case, first name has the deletion neighborhood computed. Again, you're exploding your data set. So one record here is turning into, 6 records. Because in this case, the first name had 6 letters. But when you combine those two, then you wind up with a pretty powerful fuzzy match index to search against. Now, I said this creates a lot of records. This is the formula for figuring out how any one record would explode. And that one record could be just a string, or it could be a record with a certain number of field groups. I'm not going to go into everything here, but this this technique that I'm showing you has the concept of a maximum edit distance rather than an exact edit distance. So if you wanted to index your data set with an edit distance of 2, which means 2 items of information could be thrown away, what will actually be indexed is an edit distance of 0, which is the exact match, and then a version where it's 1 and a version where it's 2. So you get everything. Hence the summation here. Some concrete ideas or some concrete numbers for this. So a starting count of a little over 450 million, and I'll explain where that's coming from later. But given that number of records, we took that think it was first name, could have been last name. And we created the one string with an edit distance of 1, and that 450 million ballooned into 3.5 billion records. Then when we did the field group version of the edit distance, the 3.5 became 12.5 billion records. Now, it's not as bad as you think. I mean, that's a lot of records, but it's extremely simple. I mean, it is a 2-value data set. It's a hash value mapped out to an entity ID. Each one of them are 8-byte numeric values. They're basically unsigned long longs. The compressed version of that is 100 gigabytes. It does not compress well because the hash value tends to be kind of random. So the compression is much less than you think, but it was still about 100 gig. And I note here that it's the simplest link structure possible. That's because it's going to tell you just a direct link, but from one record to another. And I'll show that here. So this is a very simplified diagram, but let's say we only have 4 entities. After running our deletion neighborhood algorithm that I showed you, we only wind up for each one of them, we have 4 hash values, and that's what is inside of each circle, right? So it's pretty trivial to look and see that there's a couple of links here. So entity 1 had a hash value associated with it of 327. So did entity 4. Entity 4 also has a different hash value that matches with a hash value inside of entity 2. Now at this point, all you know is that they do match. They could match exactly. They could match fuzzy. Odds are it's going to be fuzzy, but that's all you know is that you have a match. You would have to go in and do an exhaustive search against these two to find out what the exact match is at this point. So what can you do with this? So one thing is fuzzy deduplication, which was one of the topics of this talk. You have a large data set and you want to make sure that you've got the right kind of records in it. You might have records that should be rolled together, merged in some way, but you just can't identify them. Now, if you don't have a technique like this, you're going to have to do some kind of roll up or a self join, right? When you've got a complex data set or you've got a large number of fields in your data set, that can be a very difficult problem. You know, a roll up is basically when you somehow sort your data set and be able to compare side by side or adjacent records. That's a good way of dealing with a very large data set. But then you have a question of how do you perform your sort to make sure that actually works? And then a self join just gets ugly. You know, if you've got, that's an n by m problem or an n by n problem, it can be huge. If you've got this technique, it becomes very easy. You have made your problem big. You have a lot of records, but it's super easy to solve because you can create your hash value to entity ID index and just sort it by hash value and then check the adjacent records. Everything at that point, when you've got identical hash values, they will all link directly. And when I say direct link, I mean like a one-step link. Now you can also, with a little bit of work, perform transitive links. Transitive links are grouping relationships together, following the, connecting the dots. So if you have a relationship, like a set of relationships, like A is related to B, B is related to C, C to D, then A is related to D, right? That's a transitive link. You're following the dots. You can actually pull that off with this, a little bit of algorithmic work. So here's the relationship we had in our example. We can look some of this stuff up. So on the entity ID side, we have basically entity 1 was paired with entity 4 and 4 with 2. We assign to every pair a unique matching ID. And this ID bears no relationship to anything else in your data set. Turn around and explode that back or rematch that back to the individual entity IDs. and then group them. So entity 4 is actually part of 2 matching IDs, right? So what we can do is look at that where there are cases of an entity with multiple matching IDs and find the minimum matching ID and basically rewrite every other matching ID in that group to the minimum. That means this entity 2 becomes a 1. Now, if you construct your data set, I'm alighting a lot of grunt work on this, but if you had constructed this and put it in order, you could actually pull this off in something akin to like a shell sort type algorithm. N notation, or as far as complexity goes. But you can see now with this matching ID and entity ID that all 3 of those entities transitively link. It does work, even though my example only had that trivial example, that does work with large number of matching IDs and a large entity count. Now to pull that off well, you really need 4 indexes. So you got your hashing value to entity ID is actually the second one listed there, but you should also have entity ID to hash value, and then back and forth between entity ID and matching ID. If you have those 4 indexes, and they're all approximately the same size on disk, then you can pull off any kind of searching. You can go back and forth. That works for deduping. That also works for search, which I'll get into. Now, search and fuzzy deduplication is about the same. It's almost the exact same problem. The difference is a search, with the deduplication, you're comparing a data set, the records in a data set, with every other record in the data set. With a search, you're comparing the data set with one record that looks just like that. You can take a web form and create a 1 record data set that looks just like your original and search on it. That's the idea here. Now, one of the really cool things about this technique is with the fuzzy matching, you can accomplish this use case that's shown up at the top. So you have a use case where you have an entry form where some fields are required, others are not. But if the user enters more data, the more data they enter, the better the search. How do you pull that off without a lot of indexes or a lot of, consecutive searching with filtering, large having statements, something along those lines? You can construct an edit distance that is basically the total field count minus the required field count. That gives you an edit distance. And then you can index your dictionary, your original corpus data set, using that, and then use then apply that exact same technique to what the user's entering. The advantage is the code that you write for creating the index and for performing the search is the same code no matter how many fields you have or what combination of required and optional there are. It's the exact same code. It's just parameters. And it's fast. Now, concrete examples. Written using our own technology, the HPCC systems, it's an open source big data technology. It's been around for a while. I encourage everybody who's never heard of this to go look at it. It's pretty interesting. Using our own technology, here's some concrete examples. And I used a 400 node cluster for actually creating indexes and performing the fuzzy deduplication side of these tests in a single node Roxy. And Roxy is basically a high-speed B-tree type retrieval engine. It's very, very fast. The indexes are constructed with the Thor engine, which is our big 400 node technology. Given our technology and given some data, I had 1.4 billion records, and I filtered it down so it was a full data set. So using first name, last name, these are all anonymized fake data, but first name, last name, social security number, street address components, zip code, date of birth, all the fields were fully populated. I wound up with a little over 450 million records out of this anonymized data set. And then I chose some test criteria, which is the first name was expanded with an edit distance to account for typos. I did combine all the street address components, and I wound up with 6 total field groups. On my 400 node Thor, it took 12 minutes to create this. Now that's, that says something about the speed of HPCC systems, but it also says something about the simplicity of this algorithm. It's not hard. It's trivially parallelizable. None of the index creation, well, there's one part of the index creation. That's when it comes down to some of the rewrites. Involves cross-node chatter. You can distribute your data as far as possible, and basically 90% of the work can be done independently, which is great. So we wrote it in 12 minutes, and it took about 400 gigabytes in space, those 4 indexes we talked about before. The actual deduplication of the 450 million records took less than 5 minutes on that 400 node Thor. Again, when you've got exact matches, which is what the index creation provides you, then you can partition your data across nodes or across workers such that there is no fuzziness in that level of matching. Even though you're fuzzy matching, your matching here is concrete, it's an equality. So you can partition on those values, and then you can do basically local roll-ups. That's why it's so fast. But in less than 5 minutes, we found out of the 450 million records, 26 million records could be put together into clusters, and the cluster population ranged from 2 records to 1,153. It was the biggest one we found. Going back to the form search, again, it's the same thing as fuzzy deduplication, but it is on one side, instead of a full data set, you have a data set of 1 record. And you can see the criteria. I just used basically the same data, but I computed a different edit distance to account for the form field, and then tested. It was a randomized test, so we came up with a lot of different queries, and we automated the test, the submission of that, and then timed the responses. Again, this could be more of a performance of HPCC, but everything came back in less than 2 seconds, which is not bad for a fuzzy form search. And that criteria that I was talking about, where you don't know ahead of time what values a user is actually going to enter. How are they going to fill out the form? Now that, I think I might have went a little fast. I'm finished. I'm going to leave the appendix up if anybody wants to take a look at this. And again, inside the chat are the PDFs, so you can download it from there. And I'd like to open up this for questions. So if there are any questions, please post them in the Q&A chat, and I'll read them and try to answer them. Let's see. Oh, there's one. Could this be used to restore missing parts of words in ancient texts? I hadn't thought of an application like that. I'm not sure if that would be possible. I mean, I would think you would need to have a corpus that would match what you're looking for before it could do that. But I mean, that said, it is not an algorithm that is confined to dataset records necessarily, nor is it confined to something like people. So anything that you could represent in multiple fields or discrete fields, or look at it a different way, features, right? You've got features of objects, then you can use this to basically do a fuzzy match on. So you can do genome expressions or something along those lines. You can also run different versions of the exact same thing. Oh, and that reminds me of something that I missed. So we talked about these deletion neighborhoods. That's basically a brute force way of slicing and dicing your data vertically, right? There's no real law that says you have to be completely brute force. That deletion neighborhood based on a string, the string-based deletion neighborhood, I should say, is just basically blindly deleting individual letters. You can apply a different kind of technique to that. You can do a fumble finger technique, right? So given the letter R on a QWERTY keyboard, what is the most likely misspelled letter? You can come up with a algorithm that creates variations of a string based on that or whatever. The bottom line is if you can bring it down to the index pairs, the hash ID, entity ID, index, then you can add them to this technique. You can make an additive, basically it would be like a giant OR where you've got deletion neighborhood, fuzzy matching, or a fumble fingered matching technique, or whatever else you have you've designed. You can also do that with the field groups. You've got one set of field groups. You can, and that falls down into a matching pair of hash IDs. You could design another edit distance deletion neighborhood for field groups that use a different set of fields. And when you compute those, they come down to that pair, again, that same pair. And as long as they use the same entity IDs, you can just concatenate those two indexes and treat them as one. What you wind up with is an OR. So one search, and you would be searching one case or another case. Let's see, another question from Tina. Can this be used for mostly numeric variable data sets? Also, can this be used for very large data sets? So mostly numeric, yes. However, the string-based deletion neighborhood is really just for strings. Now, again, you can use a different one. I said the fumble fingered. You can create your own deletion neighborhood, basically, where you create variations of the values. So you can use that to transpose a number into a rounded version, for instance. So you could collect a range. There's a lot of different techniques around this, but it basically comes down to creating variations of records and then indexing them. Very large, yes. So that was one of the things I showed you. 450 million is large. I've successfully used this on much larger ones, but I didn't have very good timing information that I could put into the presentation. But yes, it's very well suited to distributed processing. See, she went on, does this result in probability of matching? No, it does not. So what it does really is it constrains the number of fields you need to exhaustively look at. So instead of having 3 billion records that you have to search for, it'll bring it down to 1,000 or something. It depends on the edit distance. So it brings it down there, and then you have to go through it and can compute. At that point, you can compute the probability. Let's see, if you've looked at using this technique for searching diseases, similar with ontology help, fast search is critical in the emergency room. That is an excellent idea. I think it would be great if we did something like that. See, another one is your hash is stored centrally or distributed after it's created. If distributed, who is managing the sharding and rerouting? Am I using TF-IDF? So the indexes that I cited here are built and maintained by HPCC systems. You'll have to read up the whole architecture for that. But it is it's about a 10-year-old open source big data platform. Is actually created by LexisNexis. It is distributed. It's distributed as large as your nodes are. So in the case, I had a 400 node cluster that created the indexes and only one Roxy node to read them. But the 400 node worker that created the indexes created 400 parts. And my one Roxy compute node, if you want to look at it that way, was referencing 400 parts at a time. Those parts could be distributed or locally. In my case, they were local. It's not TF-IDF. That would be something, again, I think you would have to go into, I mean, that's term frequency, right? It's not an inverted index. This is literally just lookups. It's numeric lookups, so it's B-tree. Let's see, I think that's it as far as the questions go. I think I might be out of time as well. If there are any other questions, please post them in the chat. If not, yes.
Dan, there is a questions area, and there are some questions that are in there actually.
Oh no.
Yeah, if you'd like, I can read those to you. Give me
Where
just
are they? I was reading in the Q&A chat.
Let's see. There's a question that says, hi Dan, what programming language are you using on the HPCC cluster?
So that is, and that's actually cited on my appendix slide here, the very last one. ECL is the language of choice under HPCC. ECL is a declarative language. It's very easy to be translated into something that can perform distributed execution, which is exactly what Thor and Roxy jobs on HPCC do.
Okay. Here's one that came in. Not sure if this was covered before, but how to create the indexes.
Not sure about that. So the creation of an index inside of HPCC is like a one-line thing. I mean, you create a data set, which is, you can think of a data set as a lot like a distributed data frame in R, okay? And you basically, inside of ECL, you declare what your index, what fields you want to index on, and here is my data set, and it builds the index. That's it.
All right, here's another question for you. Can this be used to detect a sanctioned person among a large number of individuals?
That is a subject matter expert kind of question. It will help detect fuzzy match, right? So if you have a list of sanctioned individuals in one data set and you have a candidate individual you want to see is on that list, this is one way of looking that up. It will certainly match partial information or mistyped information, things like that. So if you've got data sets where somebody is a Daniel in one and a Dan in another, it could conceivably match between those two. If you also have, for instance, like a nickname kind of lookup as one of your deletion neighborhood type filters. So it's possible to build that, I think, out of this. It won't do some of the more interesting things. I mean, there's a lot in person linking in particular that is not easily accounted for algorithmically. There's like geographical proximities and things along those lines that this kind of algorithm doesn't address.
All right, and it looks like we have one last question. And this is, do you have plans to post code examples on a GitHub repo?
That's actually on the very last item on my appendix that's being shown right now. So that is an ECL version of what I just described. It exists as a library, not as a running application, but it is a library. At some point, I may post a different language version of the algorithm. Not sure. At this point, there's only an ECL.
Right, and that's the last question we have for you, Dan.
Awesome. One more appeared in chat. So does it support semantic search? It doesn't out of the box. That would have to be another deletion neighborhood type of search you can add to it. But again, you can build it and add it. The technique is there. And if you can, that's pretty interesting in that you could add that and add it along with everything else. And as I said, make like an OR version of a search that runs at very high speed, assuming you have a system that can handle the data. This is awesome. Okay. Well, I think we are perhaps finished.
I think we're done. Dan, thank you so much for this wonderful presentation.
Thanks, everybody. Thanks for listening. And if you have any questions, please feel free to reach out, contact me.
Okay, thank you for speaking, Dan. We are grateful to those who have attended the session, and we'll now start our short survey. This short survey helps us to shape future conference. Thank you guys so much.